SI. So the course is sponsored and organized by National Innovation Center that belong to Ministry of Planning and Investment. So I would like to introduce and present Mr. Vũ Xuân Hoài, Vice Director of NIC, that can give us some opening speech, please. Xin mời anh Hoài cho một vài lời phát biểu về với các em học sinh và các thầy ở trong này.
Vâng, chào các anh chị. Rất là vui được gặp các anh chị ngày hôm nay. Và trước hết thì cũng rất là cảm ơn sự tham gia và đồng hành của FPT, của Tresemme, của đối tác cung cấp cái phần mềm cho chúng ta là Cadence và Đại học Bách khoa Đà Nẵng, Đại học Công nghệ Thông tin Thành phố Hồ Chí Minh. Thì như chúng ta đã biết thì hiện nay thì đối với cái ngành công nghiệp bán dẫn ấy thì là một trong những cái lĩnh vực trọng tâm được chính phủ và đặc biệt là Thủ tướng Chính phủ rất là quan tâm và ưu tiên lớn nhất để phát triển cái ngành này đấy là phát triển nguồn nhân lực. Chính vì thế thì Thủ tướng cũng đã giao cho Bộ Cách Đầu tư và cơ quan đầu mối là Trung tâm Đổi mới sáng tạo quốc gia NIC để xây dựng cái đề án phát triển nguồn nhân lực cho ngành công nghiệp bán dẫn đến năm 2030 và định hướng đến 2045. Thì trong đó mục tiêu đến 2030 là chúng ta có khoảng 50.000 kỹ sư. Thì trên cái cơ sở đấy và qua các cái buổi trao đổi làm việc với các đối tác cùng tham gia tổ chức thì đây là một cái chương trình mà được cái sự hỗ trợ rất lớn và đồng hành của các cái đối tác mà tôi vừa chia sẻ ở trên để mà tổ chức được các cái chương trình đào tạo để đặc biệt là cho những cái học viên mà tham gia cái khóa đầu tiên này thì chúng tôi cũng tổ chức một cái chương trình để lựa chọn rất là khá là ờ, gọi là cũng cạnh tranh, có sự cạnh tranh cao để tìm những cái ứng viên xuất sắc và phù hợp cho cái chương trình đào tạo. Tôi cũng hy vọng là sau cái trong quá trình đào tạo thì có cái vấn đề gì thì cũng có thể là mời các anh chị học viên cứ thẳng thắn trao đổi thêm với các chuyên gia tham gia đào tạo trong cái chương trình của chúng ta. Đồng thời thì cũng như là có các cái đóng góp để làm sao cho cái chương trình đào tạo của mình ngày càng tốt hơn và cũng như là sau khi tốt nghiệp cái chương trình thì cũng có thể tham gia được các cái chương trình phát triển đặc biệt là các cái sản phẩm thiết kế chip cho Việt Nam trong cái thời gian tới. Tôi cũng rất là mong muốn là sự tham gia của các chuyên gia tham gia chương trình cũng như là của học viên cho cái đề án chung về phát triển nguồn nhân lực ngành công nghiệp bán dẫn đến năm 2030 như tôi vừa chia sẻ ở trên. Một lần nữa thì thay mặt Trung tâm Đổi mới sáng tạo quốc gia, tôi chúc cho các anh chị học viên là nhiều sức khỏe và cũng như là hoàn thành xuất sắc khóa học. Và cảm ơn các anh chị chuyên gia để là tận tình và cũng như dành rất nhiều cái thời gian quý báu của mình để tham gia cái chia sẻ trong khóa học này. Xin cảm ơn.
Cảm ơn anh Võ Xuân Hoài.
Vâng, thì xin chào các anh chị học viên, chào các bạn sinh viên. Thì như chúng ta đã biết là chương trình này nó là một sự nỗ lực rất là lớn của chính phủ và thông qua Bộ Kế hoạch Đầu tư và cụ thể là thông qua Trung tâm Đổi mới sáng tạo quốc gia. Và với cái việc chuẩn bị từ đúng vào cái dịp khánh thành cái tòa nhà của NIC tại khu công nghệ cao Hòa Lạc cho đến nay ấy, thì chúng ta cũng đã có một cái thời gian là hơn 4 tháng để có một cái chương trình này. Thì bên cạnh những cái chỉ đạo điều hành của Bộ Kế hoạch Đầu tư cũng như là Trung tâm Đổi mới sáng tạo quốc gia thì khóa học này không thể thành công khi mà thiếu vắng được những cái đội ngũ chuyên gia, đặc biệt là đến từ các cái chuyên gia đến từ các tổ chức mà đồng hành cùng với NIC như là Tresemme, FPT và các cái trường thành viên, ví dụ như là trường Đại học Khoa Đà Nẵng, trường Đại học Khoa Đà Nẵng, trường Đại học Khoa Đại học Đà Nẵng, trường Đại học Công nghệ Thông tin, Đại học Quốc gia Thành phố Hồ Chí Minh và một số các trường đại học công nghệ khác. Thì tôi muốn nhân cơ hội này để các bạn sinh viên cũng biết được những người đứng đằng sau những chương trình này. Thì tính đến nay là chúng tôi đã có khoảng hơn 27 cuộc họp, 27 cuộc họp cũng như là có rất nhiều lần bàn tán và phần lớn là vì những chuyên gia ở Texas Hoa Kỳ và Việt Nam có sự chênh lệch về giờ giấc, nên chủ yếu là những cái giờ giấc nó họp nó khá là thú vị, và cũng đòi hỏi cái sự gọi là hy sinh của những anh ở bên miền Hoa Kỳ. Thì tôi muốn giới thiệu, tôi muốn share cái màn hình này để các bạn biết là những người mà đứng sau ở chương trình này ờ, là ai, và chúng ta sau này thì chúng ta có thể chúng ta sẽ gặp những con người ở ngoài đời hoặc là không. Ờ, anh feel cái share màn hình, share đây, share. À, vâng, thì như các bạn đã biết là bên ngoài cái cơ quan tổ chức là NIC, là Trung tâm Đổi mới Thác quốc gia thuộc Bộ Kế hoạch Đầu tư ấy, thì chúng ta có các cái tổ chức như là tổ chức CHSMI, trường đại học trường đại học Bách khoa Đại học Đà Nẵng, trường đại học Công nghệ Thông tin, ờ, ừm, Đại học Quốc gia Thành phố Hồ Chí Minh, và đặc biệt là công ty FPT. Thì chúng ta sẽ cùng gặp gỡ cái đội ngũ mà đứng sau cái đội ngũ tổ chức mà đứng sau cái việc chuẩn bị cho cái khóa đào tạo này. Thì tôi muốn trân trọng giới thiệu và giới thiệu với các bạn là có ông Nguyễn Vinh Quang, vừa là đồng sáng lập vừa là CEO của công ty FPT Semiconductor. Các sản phẩm của FPT Semiconductor thì các bạn cũng đã biết. Ngoài ra thì có một người vừa là người anh của tôi, vừa là người thầy của rất nhiều thế hệ của những kỹ sư mà thiết kế bán dẫn tại Việt Nam. Đó là ông Phi Hoàng, là người sáng lập ra tổ chức Chasami, có trụ sở tại Texas, Hoa Kỳ, là người mà đã dành rất nhiều tâm huyết cho cái việc mà đào tạo lên nhiều thế hệ kỹ sư thuộc nhiều công ty khác nhau tại Việt Nam trong cái lĩnh vực này. Ngoài ra thì đấy là bên ngoài cái hai cái tổ chức là thuộc công ty, thì chúng ta thấy rằng là không thể khóa học này không thể thực hiện được nếu như mà không có sự đồng hành của các thầy đến từ các trường đại học. Thì tôi cũng muốn xin giới thiệu với các bạn là có mặt trong cái buổi học đầu tiên ngày hôm nay của chúng ta, mặc dù rất bận rộn nhưng mà Phó giáo sư tiến sĩ Nguyễn Hồng Hải, Phó hiệu trưởng trường Đại Bách khoa Đại học Đà Nẵng cũng có mặt. Và thầy Hải là chúng tôi nhận thấy rằng là thầy Hải là những người mà là những yếu tố tích cực nhất mà thúc đẩy cái chương trình này nó thành công. Ngoài ra thì có thầy Nguyễn Minh Sơn. Thầy Nguyễn Minh Sơn hiện nay, tiến sĩ Nguyễn Minh Sơn hiện nay đang là trưởng khoa kỹ thuật máy tính thuộc trường Đại học Công nghệ Thông tin, Đại học Quốc gia Thành phố Hồ Chí Minh. Thầy Sơn được trên cõi mạng thì được mệnh danh là Sơn Hardware, và là một người rất là tâm huyết về về vấn đề này. Ngoài ra thì có tiến sĩ Nguyễn Văn Trung. Thầy Trung thì hiện nay đang làm tại Viện Tích hợp Công nghệ thuộc Học viện Viện Học viện Kỹ thuật Quân sự, có tên giao dịch là Trường Đại học Kỹ thuật Lê Quý Đôn. Và tôi thì mặc dù là tôi với anh Trung thì không có tên trong các cái đơn vị đồng hành, nhưng mà cũng góp chút gọi là công sức để mà có thể kết nối các bạn và kết nối các thầy cô. Thì tôi là Mai Anh Tuấn, hiện nay tôi đang công tác tại trường Đại học Công nghệ thuộc Đại học Gia thuộc Quốc gia Hà Nội. Và tôi muốn dành một cái sự tôn trọng ở cái slide tới đây cho ba cái người, các thành viên mà tích cực nhất, bao gồm hai cô gái rất là hai cô gái mà luôn luôn gửi vào minute meeting, tức là những cái biên bản cuộc họp cho tôi vào lúc nửa đêm. Đó là chị Đinh Thị Kim Ngọc, người mà trả lời cũng như là trả lời các cái email của các bạn rất là tích cực. Ngoài ra thì có chị Lương Thị Nhung, và anh đặc biệt là anh Quang Phương, là ba nhân vật này thì đều hiện nay đang làm ở FPT Semi, tức là FPT Semiconductor. Và anh Phương thì là người phụ trách các vấn đề, tất cả các vấn đề liên quan đến cloud server, rồi các vấn đề về kỹ thuật khác. Thì đương nhiên trong cái khuôn khổ thời gian nó không cho phép, ủy ban tổ chức chỉ cho tôi có 15 phút thôi, tôi không thể nói hết được. Ở trong này thì chúng ta có thể thấy rằng là với các cái tiền tố là TA, thì các bạn có thể thấy những ờm, cá nhân mà đến từ các cái tổ chức, và đặc biệt ở đây ví dụ như có ông Dave, Dave, can you raise your hand, please? Ông cũng vừa là bạn vừa là những gọi là thành viên sáng lập của Cheshire và đã giúp chúng ta rất nhiều, và chúng ta thấy rằng là hiện nay giờ Mỹ đang là mấy giờ anh Phil ơi?
Giờ Texas là 8 giờ tối.
8 giờ tối thì chúng ta thấy rằng là giờ ăn tối đấy, giờ gọi là vâng, tôi đang
Nhưng mà
thấy
em hiện tại đang ở thành phố Hồ Chí Minh, đang ngồi chung với Nguyễn
vâng.
Minh Sơn trong Đại học Công nghệ
Vâng,
Thông tin.
thì chúng ta sẽ dành một vài phút để dành cho các thành viên. Tôi cũng không chưa hân hạnh được biết hết, thì có lẽ là anh tôi vừa nhìn thấy anh David. David, can you say something?
Yes, sir. This is David Campbell in UIT.
Yeah, mute all the laptops in there, right? Yeah.
This is David Campbell. I'm at UIT and a member of Trace Semi. I appreciate Dr. Sun and everyone who's hosted us here. And was this you were ready for our prepared set of transition fill into the presentation, or was that just an introduction of me?
It's still introduction. Yeah, I don't know what else doing is happening. Yeah.
Yeah, well, I appreciate
Yeah,
to be here.
yeah. Okay, so in addition to David, Thiện, are you there?
Oh, hey, yes, I'm here.
Okay. And Dave, can you say something? Dave, please say something to us.
Dave actually has a presentation at the beginning of
Okay.
next session,
Okay,
so
okay.
maybe we'll
Okay,
wait
okay.
from him then. Yeah.
So, okay, before the class start, I'd like to introduce and present you some regulation and also the timetable for you within the class. So, okay, I like to share my screen. I hope that you already received how to say the timetable for the theory and lab within 15 weeks. Okay, I say in Vietnamese. Tôi hy vọng là các bạn đã nhận được các cái tài liệu mà phổ biến cái lịch học ở trong vòng 15 tuần. Thì chúng ta sẽ có 2 buổi lý thuyết và 2 buổi thực hành trong một tuần. Thì giờ lý thuyết là bắt đầu từ 9 giờ cho đến 11 giờ vào ngày thứ ba và ngày thứ sáu hàng tuần. Còn vì các bạn học viên thì được phân bố ở 3 miền, miền Nam, miền Trung và miền Bắc. Do đó là lịch thực hành tại các cái điểm tại các cái địa phương ấy thì nó có sự thay đổi một chút. Thì các bạn thuộc thành phố Hồ Chí Minh, theo khu vực miền Trung, cụ thể là Đà Nẵng và Hà Nội, thì sau này sẽ nhận được một cái email chung. Sau đó thì các thầy tại các trường đồng hành ấy sẽ hướng dẫn các bạn thực hành theo những cái giờ mà đã được quy định. Thì cái tuần này ấy, thì chúng ta chỉ có 2 giờ thực hành thôi, tức là chủ yếu là chúng ta sẽ làm quen với phần mềm. Và cái tuần sau thì chúng ta có 4 giờ thực hành. Còn từ tuần thứ ba cho đến tuần gần cuối cùng ấy, thì chúng ta sẽ có 8 giờ thực hành. Và cái việc thực hành này sẽ được thực hiện tại các phòng thí nghiệm tại trường Đại Công nghệ Thông tin Đại học Quốc gia Thành phố Hồ Chí Minh và trường Đại học Bách khoa Đại học Đà Nẵng, cũng như là Trung tâm Đổi mới sáng tạo quốc gia tại Tôn Thất Thuyết tại Hà Nội. Thì nếu như các bạn sinh viên chưa nhận được thì cái thời khóa biểu này thì chúng tôi sẽ gửi lại cho các bạn ngay trong sau cái giờ học này. Ngoài ra thì chúng ta còn có những cái tài liệu về phổ biến về cái kỷ luật của lớp học. Trong đó thì như các bạn đã biết là vì khóa học này thì chúng ta các bạn ngồi đây là những người mà được lựa chọn rất là cẩn thận và có cái trình độ về chuyên môn cũng như trình độ về tiếng Anh, cũng như đặc biệt là có cái khát khao để bước vào một cái ngành công nghiệp mà nó đang có doanh thu được dự toán là hơn 1.000 tỷ đô la vào 2030. Vì thế thì chúng ta cũng phải xác định rằng nó cũng không hề dễ dàng. Nhưng với cái năng lực, với cái nhiệt huyết của các bạn ấy thì chúng tôi đảm bảo rằng là chỉ cần các bạn đi học đầy đủ thì các bạn sẽ hoàn thành khóa học này, và các bạn chắc chắn là sẽ không hối tiếc với những cái chia sẻ của những chuyên gia, đặc biệt là những người mà có rất nhiều năm kinh nghiệm trong ờ, trong việc tạo ra những sản phẩm đã được thương mại toàn cầu. Thế thì tôi nghĩ rằng là tôi cũng không muốn chiếm nhiều thời gian của các thầy là giảng viên nữa, và tôi muốn dành lại cái thời gian đấy cho các thầy làm instructor của lớp. Okay, so this time to start our class, so I like to give a position to you. Yeah, David.
Thầy cảm ơn Tuấn nhiều, thì rất là chân thành cảm ơn anh Tuấn đã nhảy vào giúp Quang điều phối những cái công việc làm của những cái người nằm trong ban tổ chức. Sự làm việc rất là cật lực và hiệu quả của anh cũng rất là được mọi người biết ơn và quý mến. Thì một lần nữa cảm ơn anh Mai anh Tuấn nhiều nha. Hẹn đi chuyến lên Yên Tử nha anh Tuấn.
Well, see you in Vietnam. Thank
Right.
you very much. Yeah, yeah.
Thank you. So let me get started by sharing the screen. Ok, mọi người thấy cái screen rồi phải không?
Yes, I'm here.
Okay. So vì lời hứa là mình sẽ làm dạy cái cuộc học này để cho hữu hiệu cho các học viên, thì mình sẽ dùng tiếng Anh nhiều, và lại một số người giảng viên người ta không có rõ tiếng Việt nhiều, nhưng mà nếu mà họ dạy tiếng Anh thì cũng có ích lợi cho học viên. Thì chúng tôi xin bắt đầu làm bằng tiếng Anh. Thì welcome to the introduction to the physical design part 1. This is a lecture 1. And we will not have time to complete them, but I'll go over a little bit about everything in this introductory 2 hours. My name is Phil Huang. I'm a founder of Trisomy, and with me a few co-founders and members that I will introduce later from Trisomy. We are a nonprofit organization started, incorporated in Texas, Austin, Texas, earlier this year in March. So this is the VR side, physical design fundamentals is a course. The agenda will be some introduction, course overview. We already went through the introduction, but will be some little introduction of other stuff. The course overview, we'll go over the course objectives and outcomes, and most importantly, the learning methodology, and touch on the physical design, what it is. So we already went through this, and thank you, Mr. Hoài, Sung Bo, and Mr. Lin, and all the members of NIC for generously helping us, coordinating everything and organizing this course. We're very honored to participate as instructors, and appreciate the effort, the sponsorship for FPT and Cadence, and also the 2 universities, Bách Khoa Đà Nẵng and Công nghệ Thông tin Thành phố Hồ Chí Minh. Really, because of all your efforts and contributions and all tireless help from different professors, we made possible this class free of charge for qualified students. And before I go through the course overview, I would like to introduce you Mr. Dave Campbell. He's a friend of mine from Austin, Texas, and he together with me and other people. He's a co-founder of Tresemme, who will open with some motivation for physical design. And Dave, you can share the screen, and before you go on, please introduce other members of Tresemme in the room with you, with Dr. Sung in UIT.
So first off, I'm David Campbell with Tresemme. Thank you for introducing me, Phil. So I may have Bob, Dr. Sun. Professor Bao is stepped just outside of camera view, but I'm sure he will be back soon. Those are the ones that we have here, along with our students and our UIT staff that is making this happen here for us.
Yeah, thank you. So yeah, but is a member of the board of directors for Tresemme, and so is Bao. And with on the line, Mr. Tung mentioned Mr. Thieng Phang. He's another member of the board, and Mr. Tung Vũ Nguyen is also with us today, helping with the class. He's a member of the board of directors of Tresemme. Dave, please go on with your presentation.
I'm going to take over sharing the screen.
Yeah, please do.
Right, why are we here? I'm going to move pretty quickly so that we can get into the actual content. But today we're going to talk about an introduction. We're going to talk about market growth, the Vietnam landscape, the chip design career, and the collaboration that's going on with all the folks that made this happen today. The semiconductor industry got started around 1960, so we're in the 7th decade, and our life now is unimaginable to those people. It's science fiction. The cell phones, computers, X-ray machines, the things that we take for granted weren't even available in my youth. The semiconductor industry is growing exponentially, and the projected growth is going to continue. Sorry.
You can use your mic. Oh, all right. Okay, yeah. Okay.
All right. Last year's revenue, or I'm sorry, 2 years revenue was over 600 billion. And by the year 2032, so less than 10 years from now, we're expected to have semiconductor industry revenue worldwide of $1.8 trillion. The dominant players in the industry right now, from a nation standpoint, the United States, Taiwan, Korea, and the Netherlands, with individual companies representing on the orders of $22 billion at the top end with Intel, but still $4 and $5 billion for other organizations and other companies. Even in its fledgling state, the Vietnam semiconductor industry had almost $4 billion of revenue in 2022, an expected annual growth rate larger than the worldwide growth rate of 12.6% from 2023 to 2028. The projected over $8 billion annually by 2028. Over 40 multinational corporations are already present. And already working in Vietnam are 6,000 or more engineers in the semiconductor industry. And the need and plan is to grow 50,000 more engineers by the year 2030. Vietnam is the next semiconductor destination. And what you've heard from the people who've already spoken to you and what you hear both in the Vietnam and internationally is that Vietnam is anticipated to step in and take over a large portion of the need for the worldwide semiconductor industry. It's a high-paying career no matter where you go, but even in Vietnam, this information is a little bit dated, but for a beginning IC design engineer, you can expect an average salary somewhere between 24 and 35 million Vietnam dong per month. With experience, that goes up pretty dramatically. And when we compare those numbers with 10 to 15 years of experience compared to the current Vietnam average worker salary of 7 million, it's a lucrative and we hope motivating for you industry for you to get into and to complete this course successfully. Recently, this was a set of job postings in Vietnam showing the shortage and the need for engineers at this moment. And you see that it's in the thousands at the different sites to find employment. We're excited about this. We're excited about the alignment of the NIC, FPT, Trace Semi, and Cadence. We're excited about the way that the Vietnamese government, industry, higher education, and students are aligning towards getting educated and filling the need. It keeps getting expressed as Vietnam's plan for 50,000 engineers by 2030. But I really want to emphasize that this is a worldwide need that Vietnam have 50,000 highly qualified engineers by 2030. And we're hoping to get you there with this course. Phil?
Thank you, Dave. So we very excited to help NIC with this national programs and with the experience that we have in the instructional staff. We hope to help NIC, Lin, Mr. Huai, and all, Mr. Thuye, and all the people, Mr. Thuye, all the people at NIC. They have a charter, a national responsibility to train 50,000 people, engineers by the year 2030, and we cannot be in a better place. So it's an honor to work with the NIC and FPT and Cadence and all the universities. So let me share the screen so that we can go forward with the rest of our program. Let me see, where's the share? Okay. Okay, do you see the right screen or no? Do you see the course overview?
Yes.
Okay,
And
thank you.
Also the next slide as well.
Oh, okay, so this is a wrong swapping. So that's a right swapping, right? So now you only see one, right?
Let's see the next slide. You need to put in presentation mode.
I want just to have no next slide. Is this the one? Let me reshare. Stop share. Screen. There's so many of them. That's the wrong. What do you see now?
We still see bots.
Okay, let me just share the screen. I have too many things open. So let's do a share screen 3.
It's okay now.
Okay, is it okay now? Let's see.
Yes.
Okay, all right. So just a reminder of a course overview. This course, after the objectives of this course is to teach you the principles of VLSI physical design. That means floor planning, power grid creation, placement, clock tree synthesis, and routing. Nothing special, is a traditional, but very fundamental and very deeply specialized. And this requires a lot of knowledge and experience and fundamental understanding of the whole VLSI spectrum. So with the focus on developing the skills, just filling the gaps between really the academia and the industry. So we want to teach at the end some basic skills to be for the students to be able to analyze and optimize performance, power, area, and also provide reliability and manufacturability and speed up the time to market for the IC design. And last and not least, we have hands-on experience working with Cadence Innovus tool for physical design and analysis. So the prerequisite is very important, but we don't expect everyone have this. But since the subject is very highly specialized, and since the target is for the students after after completion of the class be able to work not only for companies in Vietnam, but also NIC and the nation also target working abroad, meaning that the students can go work in United States or other countries. The world is facing shortage, serious shortages in terms of IC design workforce. So English is essential, and we want to teach in English. We realize that it is very important. Sometimes you just miss the concepts, but weighing out the pros and cons, teaching in English is still the best option going forward. And so another prerequisite will be the understanding of digital logic design. We don't have time to teach you what a NAND gates, NOR gates are, what the logic gates are, sequential combinational circuits. So we expect you to know that. If you don't know that, we will provide some links for you to catch up if you don't have an opportunity to take classes related to those topics. And also very key is the basic knowledge of VLSI, very large scale integration concepts. So we need to know of electronic devices like transistors, diodes, resistors, capacitors, etc., inductors. And also the transistor level logic and circuit design and the fabrication processes in semiconductor manufacturing and basic IC architecture. So this alone, you probably need your bachelor degrees and master degree. So however, the good news is that these things you can teach yourself if you don't have the opportunity to take the classes. So, but if we don't have these concepts, it's very difficult to understand the physical design, because as you will see, physical design, even though to some it's just a push button, but to do it right, it requires a word of knowledge. And also sometimes students don't get opportunity to work even in the Linux operating system, and a background in the scripting language will help. As you can find out, a lot of automations have to happen when you have to place 10 billion transistors on the smart chip that will meet certain requirements that would be impossible without any automation and scripting languages and EDA tools and all that required for automating a physical design task. So the syllabus, as Mr. Man Tung shared, this one has a little bit more details. So it has the week, the dates, and the topics, and in addition to the top level topic, we also have the details, a little bit details, but I'm not going to go over everything, but this as a reference for you, so that you know certain week we're going to cover what topics, right? So basically, introduction to physical design, data preparation and import. What do we need to do to prepare for the input? And the first step in the physical design will be floor planning, and after that, we will go through the process called placement. and then we go through the process of building clock trees and do the routing and export the results. So you'll be exposed to different aspects of it. And keep in mind, this is just a fundamental class. So you don't expect to know everything there is about the physical design yet, because it's going to be it's going to require more than just one class. But we hope to give you enough information so that by week 13, by week 7, midway through, we can introduce you a topic, meaning that you will know what the final project is going to be, and you're going to work with your team in the remainder of the 3 months to work on a real project. At the end, you're going to produce a chip. And hopefully that will be a lot of experience worthy of your time and give you better opportunity for landing a job. And we will have some final assessment of your project after your 24 hours of lab. You can see labs, typically about around 8 hours of labs per week, 4 hours of lecture divided into 2 Tuesdays and Fridays. But at the end, it's all about labs. You can work on real projects and all. And we have a final presentation assessment. Hopefully, everybody will pass. We'll have a completion certificate, but we will not have a lot of traditional exams or etc. Our goals is a little bit different, and this will be shared with you, and there are links to the syllabus that if we need to make adjustment, we're going to make it on the syllabus themselves, and you can always have this link and go and see the latest and greatest. So the course format is a hybrid or what we call a blended classroom, and we'll go over it a little bit more. But the lectures will be online, Zooms at Tuesday, Fridays, as you know, 9 to 11 a.m. And this, some of you already participating via online. So even though there's some requirements of in-person, but that requirements can be relaxed and dependent on Vietnam, whatever Vietnam decided to do. But the labs will be in person, and it's questionable whether or not it can be also online. But at 3 locations, and these are the locations at NIC, DUT, and UIT. But the specific schedules are managed by the local teams. So some of you might be confused and say, hey, these are the times that you have to be in the labs. No, these are the times that are allocated to different regions, and it's up to the local university or NIC to decide where in this time that you have to spend 2 hours of week 1 and 4 hours of week 2 in the labs, or 8 hours divided of however many sessions, for the subsequent weeks. It will be managed by your team of TAs. But, oops, sorry. Please ignore these things. But the intention here is just to give you the link to the Zoom information. If there's some loss of information, you can always have the static links, but it's supposed to be removed here. But we'll introduce you to the Google Classroom. And then there's something that how the students can work together in projects, how the TAs can help you, and etc. So this I will let Mr. Thuye, if there's some more detail, he's going to share with you. But what the learning methodology, we are using what we call the flipped classroom. So flipped classroom is a reverse, as you can see, of the traditional classroom, where the traditional classroom, you start with teacher teaching, shoving the information and things through your head, and then you take it and you go home and you do homework and you do exams. The flipped classroom is that you're going to just have a lot of exposure to information before and during class. There's going to be some practice based basically, and after we'll be processing what you learn. Basically, this is the model. So we use the Google Classroom as a platform for teaching, and we'll have a combination of pre-reading the pre-class materials, videos or recordings to review or watch or whatever before coming to the class. So we're here, you learn a lot. We're not teaching you, but we provide quality information selectively chosen for you to go through at your time. So it's called asynchronous, meaning that you can do whatever during this time, that you don't have to be in certain place at certain time. And then when we do go in here, it's a 2 hours of each time, 2 times a week. You will have something called lectures and labs. Lectures are not the traditional lectures where you go from A to Z, but based on the feedback you have on the preparation step, the teachers can selectively teach certain concepts that they think that you need to know deeply. But just to reinforce what you have learned here without the teacher. So, and then it will be just group discussion, problem solving exercises, hands-on, right? Hands-on projects and interactive tasks that facilitated by the instructors. And this one is synchronous, meaning that you have to be in class certain time of the day. And the toward the end of, if there's a section that have labs, then that toward the end we'll have sessions that we can tell you about the labs. And then during the lab is asynchronous and synchronous, meaning synchronous, meaning the TAs and the professors and the mentors will help you during certain time and in person. So, but you can spend time outside of that, asynchronously reviewing different materials that you have, either via Google Classroom or via the lecture sessions. So the lab will be guided, and you work in groups that maybe Mr. Tung can and go over more deeply in the following lectures or weeks when we're ready to do serious labs. But basically, it's group learning, group projects, and group QAs, meaning that the TAs and the engineers mentors who helping you with the labs can answer most of the questions, and they will do it in smaller settings at different locations. And then when you finish with this, if anything that the local people don't solve it, or anything that's worth sharing with the bigger class, then the leaders in this group will bring up to the lecture of the next day, and we can discuss in the class in a bigger group. And there'll be some self-evaluation that Mr. Tung can go over. But the key is blended delivery, meaning hybrid, meaning online and offline. And the key is flexibility. A lot of time you can study on your own schedule. So those are the beauties of the flipped classroom. So basically, this is the traditional teacher-directed learning. You have teacher, we have knowledge, go through the teacher, spread out to the students. And here with the new methodology that we are adopting at TRESemmé, and also supported by all the universities that we're working with, Mr. Tung Sung, Mr. Hai, and all the people. This is what we believe is better, right? And more suitable for what we're trying to do. So we have teachers. We focus on the students. So students divided in groups, you see here. And so either they work individually or collaboratively, and we have a community where the TAs and the engineers and the professors and the people in the industries will be helping out with sharing your knowledge, discussing and having this kind of ecosystem. So sorry for this message. It messed up the But basically, the teachers are now facilitators. We're not teaching, we're facilitating, meaning that we help make things happen. So with this system, we have assessment and feedback by having different setting like this. We have automatically assessment and feedback between the teaching and the learning people. And we have interactions between students with different people, right? Most valuable is access to the professors and industry experts. And we will occasionally, hopefully, will be able to bring in seminars or experts that in our circle to present to with some targeted presentation and workshops. We don't know how much of that we're going to be able to do, but we're trying to do some. And most importantly, in mentorship, the engineers who helping you in the labs, the professors who helping you in the labs, they are your mentors. So this is a lot better than you just take a class and you just play the videos. This is your your recipe for success. This is built for to last. Meaning, this is not just the beginning, just not the class itself, one individual class, but the intention is to keep this going, class after class, and way after you start your career. We hope to have this kind of environment that will incubate and encourage startup companies later taking advantage of all these great opportunities presented to Vietnam. But for this community, we already say you're mainly the government, the academia, and the industry, right? So you see NIC, you see huge support. They have connections, and they can help with companies that have needs, and they have nationwide, international relationship that present a ton of opportunities for the students, and also the engineers working on here, and the university DUT and UIT is just two universities that we initiated with just via accidents. But the people who Mr. Tung, Mr. Quang brought in, we saw the list of universities, including Bách Khoa Hà Nội and all well-known universities are with us right now. So I'm very excited. And then we have engineers working for FPT, HCL. These are the people who are in this room right now. Because you see FPT, a lot of engineers from all regions, north, middle, and south. We have FPT engineers. Thanks for the support of FPT Semiconductor and FPT Corporation. And we have people from HCL, people from Qorvo. Qorvo here is a special name for me because in that Qorvo, there's a person called Nguyen Hữu Quang. He's my favorite student. I taught him a while back, and he's now the manager for Qorvo and looking for to expand his team in Ho Chi Minh City. So yeah, he hopefully he will get some new hires in helping with us, people from Co-Asia, etc. And also from the USA, because of the technology, right? We're teaching online via Zoom. And we are the members of Tresemme is in USA, but we are not just a bunch of people outdated, right? And we're not teaching you from the books. We teach you from years of experience. The people who we have today in this room. The youngest one have at least 25 years of experience in physical design or in very related, and they're still working on, like myself, I work for Skyworks. And in Skyworks, if you open the iPhone, there are 2 front-end modules that made by Skyworks and a ton of filters that is still in the latest iPhones. So we work on exciting projects, and we have Tien and another person named Tao. They working for Silicon Labs. We have Bat. He works for MediaTek. He just finished a few 3 nanometer humongous chip. And we have Vũ Nguyen. He worked for NXP and he's a chief architect. He defined products for NXP. So we have real people, real experience that really a resource for you. We hope to make a difference, and we hope to be able to guide you, provide some mentorship and guidance. And there are some biographies for the teachers and all, but we're not going to go there. And we also have Dave, our co-founders. He's in the IT industries, and he's passionate about learning Vietnamese. So hopefully someday he will teach us software and IT in Vietnamese. Anyway, and then our members also is a professor from university in Vietnam. He's one of our founders as well, Mr. Bảo Võ, right? So I don't know what else I missed. So yeah, and in terms of technology integration, I mentioned something, right? We teach online via Zoom. That means we can teach internationally. Whoever experts that we need and have a passion to teach and to help the young generation. Our goal is to develop the next generation we call leaders for semiconductor. So we're not only trying to develop just a worker earning money. We want to develop leaders that need it for the next generation. So we want to have the best out of the best, and via the technology we can get those people to participate and help you out using Zoom. And we also use the latest and greatest Google Classroom to manage this flipped classroom that you can see in the future. And then with the support of FPT, we bring the other labs on the cloud. This is one of the things that make me happy quite a bit, because at the beginning we were planning on having the other labs in each of the 3 locations on a machine of server somewhere. But with the new idea, if we say, with the support of Cadence, we've brought them, and with the support of FPT, who is paying for the cloud, we get everything up and running on the cloud. So when you do the what do you call it? You do the labs, you're going to be working on the cloud. And we have Mr. Phương here, who is very good. I'm very impressed of what he did in a short time to bring us up all the tools and data up on the cloud. So, so I think that's all I wanted to cover before we dig deep into the place and route, and that brings us to close to the hour. But I want to add something here because of this flipped classroom. You'll be asked a lot of questions. The purpose of the question is to probe for understanding and to assess what you know and what you don't know, what you need to know to guide our activities in class. So the ability to answer questions either in Google Class or live via Zoom is important. So we'll have a lot of multiple choices to encourage the interactions. And we need to talk about how the students can ask questions, right? Because you have a lot of people in this room. So what is the best way to ask questions? And maybe we're going to take a 5-minute break, and after that, Thuye, Mr. Thuye, if you have some information about how people can work in the lab session and how they self-evaluate, we can talk about that, or we can save for the Friday. Maybe that's what we need to do so that we can cover the rest of the information on what is physical design. Okay, so yeah, I am not sure what the best way to ask question yet, but maybe did we have any question in chat, or maybe we can open up for one question before we go on to the break. Okay, so yeah, so if so, let's take a 5-minute break. Let's get back at 8:05, and but or someone, can you just do a countdown, a clock showing, and then we have a bathroom break, and then we promptly restart at 8:05.
We will restart in 2 minutes.
Ok, bây giờ chúng ta sẽ bắt đầu lại. Thì mọi người đã có câu câu hỏi gì không? Có feedback gì? Thì có một số người thì cũng nói là nên nói chậm lại một chút xíu. Và nhưng mà không biết là mọi người có câu hỏi hoặc là có đề nghị gì không trước khi mình bắt đầu cái phần tới. Okay. TA, when I'm presenting, I don't see the chat and I don't see anything. If you see anything that need attention, please let me know. I don't see your text either. So, yeah. Okay. So let me share the screen. Okay. Can you see the screen?
Yes.
Okay. Okay. So, what is physical design? As you know, uh, we can start with the very high level. So if you have a product, idea like an iPhone, right? So typically, you do market research and then you do system specification. What does it look like, and what features does it have? And then you would partition into hardware and software. So software and hardware are developed in parallel, with the software, doing stuff that software does, and the hardware goes through different design styles to get a chip. At the end, the system, are combined together, and some system testing is done, and then you have on the hardware side, you have a chip, for example, like a 17 Pro chip. that can be put on a board and put it into this iPhone 15 Pro. So physical design is somewhere in here. It's we call application specific IC. The reason for the term application specific is just design is the general purpose that can be used in any kind of product, kind of targeted at a specific product like a phone, a cell phone. So it's called application specific. I'm not going to go over the rest of the style because of the time constraints, but you can find out what are the implementation or design styles or methodology that is used other than just ASIC. Right. So I jump right in this ASIC. What does that involve? So the ASIC development flow, basically ASIC is cell based. We'll go over why it's called cell based, but this is how a chip is built. Simplified flow of it. So you would go through the specification process where the marketers, go do market research, and out of market research, there's a document called marketing requirement document. It's called MRD. And so our people, Vũ Nguyen, who works for defining product for NXP, he's in this space. So we create the market MRD and then also what we call a product specification, product requirement documents that define what does a chip do, how fast does it need to operate, how much power will it consume, how big will it be, how much will it cost. At the end of the day, can you sell a lot of chips and make money, right? So define what the market needs and what people will buy. And after that, what we call front-end design and back-end design. And with this, there are varieties of definition, but this is what we go with. So the front-end design involves architectural design, microarchitectural design, and RTL design. And this thing is nothing new. This is very typical, but it's just a way to explain the process for those who not exposed it yet. So architectural design and microarchitecture design, you will have some kind of architectural level, what we call abstraction. This is a key concept that you need to understand, and why you have different levels of abstraction. What does that mean? Why we need it? But we'll go over why. But basically, the result of these steps will the design, the same chip, right? The A17 Pro is represented differently at different levels. So at the architecture level, at the RTL level, we'll know what RTL is. At the gate level, transistor level, at the physical level. So the front end involves architectural and microarchitectural design, and then RTL design, and the back end, we call back end, involves turning of an RTL design into the gate and transistor and physical representation before being sent to the manufacturer. So the process called logic synthesis and circuit design. Sometimes you don't do this, and the circuit design is not in the flow, but it's done via an IP development process. And then the final is a physical design. So at the architectural level, you will do, you answer the question, does the chip have all the required functionalities? After you specify what the chip looks like, now you implement it at a high level. With this high level, does it have all the required functionalities? Is the design adequate for meeting performance goals? Meaning that sometimes, if you don't design the architecture correctly, there's no way you can meet the performance goals. And we know what performance goals are in physical design later. So it's interrelated because a good job in the person who does the RTL and architecture design need to know the limitation and the capabilities and the possibilities or feasibility of the backend design. The backend design involves turning from logical to physical implementation that basically answer the question: does a chip meet all the required performance specifications? So physical design is the last step of the entire design process in ASIC development flow, and it answers the questions: does a chip meet all the required performance specifications? Right. So what are they? So the primary goals of physical design is this: it encompasses optimizing integrated circuits for superior performance, minimizing power consumption, and efficient chip area utilization. Basically, you heard about PPA. PPA optimization, meaning finding the right balance between three factors to achieve an optimal design for a specific applications or use case. In this case, for example, for A17 Pro chip, right? In a cellular phone. So what performance means, how many cores, what the speed, etc. So this is basically in the overall processing capabilities. Can you optimize it? Can you enhance the performance? You can beat competition in terms of functionality, processing capabilities. And can you meet timing constraints? The cell phone needs certain gigahertz to realize the real life applications. Can you meet that constraints? So you will define with the performance, your chip, therefore your system is more powerful. Another P is power. So the second goal is to minimize the power consumption. The purpose for this is to extend the battery life, right, and to reduce the energy cost, right, because batteries, obviously, if you consume less batteries, your products worth more. And for products that really fast and powerful, they can be very very hard. So by minimizing power consumption, it helps you effectively manage the thermal. In some cases, will reduce your cost of cooling your system because your chip is not as hot as a competitor. And that's the last of the PPA is the area. Area relates to cost. So for the meeting the performance, beating the competition with the lowest power, and your chip is small also. So if you use small, then it costs less to manufacture. Therefore, you can sell at less price and you can compete more. But PPA you hear, but it's not all. The physical designer have to rely on the reliability and robustness of the chip. So because of the different operating conditions and environmental factors, the chips sometimes can work and then it will not work by effect of such as aging or thermal or mechanical problems, that it won't work as reliable. It works for a few months and then it doesn't work. So the physical designer have to put in the inside the layout really a design that can stand all these variations and all these environmental factors that affect the reliability and the robustness of the chip. And also manufacturability. You imagine a few thousand chips on the surface of hair. It's like it's mind-boggling. I'm in this industry for almost 40 years. That every time I think about what we are producing, it's just unreal. So, but how do you manufacture? You have all these polygons that you put together and you do simulation and everything. How do you know that in real life it's going to work, and is that manufacturable? Right? Manufacturable meaning that you will shine lights on and you make the chips, and will it produce what you want it to produce. So there's a lot of things in the physical design that you need to do to make sure the manufacturability of the chip. And last but not least, productivity. With nowadays, with any days, productivity is everything, because every year there's a consumer electronics show. Every year the iPhone needs to have a new model. Before that, the chip has to be there. And before that, all these specifications, you have a small window and you have challenging performance goals. If you don't have rapid closure of all design goals, closure meaning you meet all the constraints, then you're not going to make it to the market window, and Apple won't have a chip to introduce at the next CES. So productivity is important. Productivity relates to methodology and tools and flows. So as you know, so these are the primary goals of your physical design, and hopefully you'll learn all these fundamental things that we do in order to achieve these. If you know, instead of just pushing button, you know exactly what you're doing. So therefore you will become a leader versus just somebody who just run the tool for someone. So that's our hope. So to do it, let's visit briefly the IC design industry, because physical design involves physics, the final form of the chip, right? The final form of the chips, and to perform, to meet all the goals that we just said, it takes a lot, and the atomic level is a transistor. So not to, everybody knows this, but just to point out, so 63, the first MOSFET was patented, and most famously 71, when Intel has the first microprocessor on monolithic silicon. This called Intel 4004. That's the first microprocessor. Is in 10 micron process, which is 10,000 nanometer, and right now we're at 3 nanometer, and going lower 2 and all. So from 10,000 in not long ago, 1971. How many years ago was that? And it has a whopping of 2,300 transistors, and at the lightning speed of 750 kilohertz. And it was designed by as a side project. It's not even a main project. Some engineers say, "Oh, let me try this," and they create a chip, and they get into a calculator. It's called Busicom, as the first calculator using a microprocessor. And fast forward, in 2023, Apple came up with the A17 Pro in 3 nanometer process with 18 billion transistors, from 2,300 to 18 billion, and from 750 kilohertz to 3.78 gigahertz, and it's on the Apple iPhone 15, 15 Pro. So it's just a tremendous growth of complexity and the technology, just purely 30, 50 years. And then not long before I started in this industry in 1986. And not long ago, in the 1970s, layout was done by hand, meaning that you have pencil and paper, you draw it, and you draw and you tape it. You patch it together on this ground. So some people say this is the original tape out tape, because they use a tape to tape all these things together. Versus some people say tape out means they put it in the magnetic tape and send it out. But anyway, so we went from just doing them hand drawn layout to really automation. So it's just a little piece of history, and just a visibility into challenges of physical design, right? So this is the A17 Pro, the autonomy of it. There's a 3 nanometer chip. Maybe Bud knows everything about this, but you can see from 2,300 calculator chip, you have an SoC system on the chip. that is in 3 nanometer and 19 billion transistor, and it has a ton of different functionalities. The reason why it's called SoC because it's not just a microprocessor, but multiple processors and multiple peripherals doing different functions that you name it, everything is here, including a neural engine for AI, etc. So for this, with this tiny thing, the complexity is very, very, very much a big problem, because the complexity only grow and grow, especially now in the light of AI and all. So the challenge is the system on chip. And the challenge also the system in package. System in package means that now you do packaging just a simple package into, now you have chiplets. You have to grow vertically. You're stacking devices on top of each other to extend the Moore's law, and also to meet certain footprint needs. So the industry is going toward the system and package, starting with all these big microprocessor groups like Intel and AMD, growing to IoT, and pretty soon it will be the mainstream for chiplet design. And then, we mentioned about billions of transistors and going through 2 nanometer and 1 nanometer and below, and going to different, maybe get out of CMOS. So ultra high speed, ultra low power. So as you can see, all these things, when they just run at gigahertz, there'll be noise, crosstalk, and all, and reliability, manufacturability, yield. When the chip is so big, then the yields become a big problem, and also productivity. The complexity is growing, but design, per designer per billion of transistors are not, the productivity is not growing as much as the complexity. So those are the challenges for physical design. And the trends are really, 3D, I mentioned, right? Sub 2 nanometer. And also, as you can see here, the growth for monolithic integration. Monolithic integration meaning that on a single die, a number of transistors, right? It's like going from 2300 to 100 billions. We are here at 100 billions and going to 200 billion on a single die. But if you grow too big, the yield becomes a problem. But on the what you can see here, 3D heterogeneous integration, meaning that chiplet design, you stacking the devices on top of each other, it can grow to 1 trillion transistor on a single footprint. And also the like a 1 trillion transistors, and also you see here the chiplets, like the SoC, that is called disaggregated SoC, meaning that become too big, then you have to make it smaller so that you improve yield. To make it smaller, you make them into chiplets, and then you stack them on each other. Right here, in here is a chiplet that you have 1, 2 in parallel. This is just called 2.5Ds, where instead of the pins going from the path, you connect them via RDL redistribution layers and all these what they call they use the bumps, and they use TSV through silicon vias, etc. Mainly bring some of the passive design to the package, and the 2.5D, 3Ds. You have logic chips on top of MCU, versus 2.5Ds. We have logic chip in parallel, but the memories are stacking. Basically, it's just going vertical. But in the future, on a single die, there'll be, instead of just one single substrate, you have layers, that where you have standard cells and RAMs on one layer, and then logic gates on the other, the lower level. You have block level versus gate level on. So you have wafer on top of wafers and connecting through these vias, and this is happening. So and then also Intel for backside power is something that that Intel has been trying, and it might bring benefit in future system that may be a norm in the future. So these are some of the examples of the future trends related to physical design. So to address a lot of those challenges, and to address the complexity of VLSI in general, what are the principles? So these principles have been identified for a long time. So it's called hierarchy, regularity, modularity, and locality. And why we have these things? It's just billions of transistors need to have some strategy instead of randomly put them together and hope it works. So hierarchy means divide and conquer. So you have a complex system, so you divide into different functions, and then you divide further and further, right? So they call it modules. So this is the concept. When you go into the design directory and they call it modules, you need to know what really why module. And then but the modules you keep on breaking down until at the level where you can comprehend. I think there's some. I'm not worried about that. There's a background. It's short, but you go to the level of details that you can just start doing and then use them as a building block to build a more complex system. So the benefit of it is that these can be designed in parallel, meaning if you have a 2 nanometer, people can start working on MUX and a NOR, an exclusive, or while people working on the iPhone, 20, right, in 1 nanometer. So people can work on different levels in parallel, right? So and then the module can be reused. So this is a must. If you don't have this, you cannot design. In the past, the design on that first microprocessor, you do one transistor at a time. But this is another concept is regularity. So you divide the design in set of similar building blocks, right? So it can exist at multiple levels, like a standard cell level. Regularity meaning you have a fixed height of the cells, but variable lengths for the logic gate. For example, an inverter small will be sort of like a length of 1, and then you have a flip-flop, you have a length of 5, but the height is the same. So that's the regularity on that height. And then for all these memory compilers, you call it parameterized. They build from a regular cell to repeat themselves and to build bigger and bigger. And also you design all these sub-modules like multipliers or even a core, and you can reuse. Yeah, you can see, you can hear how this new Intel processor have 20 cores, or this NVIDIA AI have 1,000 core, for example. Those cores are designed only one, but repeated 1,000 times, right? So the benefit of it is to reduce the number of subcomponents to design for sure, right? To design, optimize, and verify, and components can be reused. So that's second concept. So the third concept is modularity, and I lost my. Okay, so you break the complex systems into smaller, well-defined, and independent modules. What does it mean? The function has to be well-defined. The interfaces have to be well-defined. Why would you want to have well-defined interface? Because when you put them together, you know what to do in terms of verification and what to do in terms of designing one block. You know the interface well, so you can design without knowing so much about the other block. So it's ease of design and independence of the design, right? And ease of maintenance and scalability and reusability. Scalability meaning that you can make it bigger or smaller, but you don't have to redesign the basic slice of it. And reusability, yeah, what it means, right? You design once and then you can reuse many times. This is an example. Embedded SRAM. So it have a standard interface, read-write address, setup time, data setup time, data, output time, and everything. Everything is very standard and modular, right? So that's, and the last but not least is the locality. What does it mean by locality, right? So it's defined here, organized and structured design in a way that emphasizes the proximity of or closeness of related components on operations. So it's kind of different things in here, but spatial mean, are they close enough? Temporal meaning that they are, in terms of timing, are they closely related? Functionality, all these similar functions or related function group together. Communication, do they talk to each other? If they talk to each other, you get to put them closer. Why you need to put them closer? Because you can minimize the connections and you make it faster and consume less power, for example. And power locality, like meaning that the power-hungry components or regions should be located and managed for minimum power dissipation. This is an example. What is this? This is a software radio. Right, so in here you have memories and you have microprocessors, you have buses, so you have IOs and all. So this bus, since say this microprocessor, these four talking to each other, and if you put this microprocessor over here, microprocessor over here, and the bus can be long, going from one side to the other. So locality means I put these four processes close together to minimize this bus. So minimizing this bus means that it can be faster, right? And minimizing this bus means it consumes less power. So it's just an example. So these are important to understand when you do physical design. When you push a button, you know the concept is going to make it a lot more interesting to you. And because of it, you understand it more, it's more fun, and it's more fun, you more creative, and you can be you can make a difference. You can be a leader instead of a follower. Right. So let me see how we do in time. So one of the key concepts is design abstractions that I touched earlier. So the concept of divide, conquer, right? So you break the design problem down into different level of abstractions and address them in steps in parallel. Key. So this is the chart, Y chart, I guess, key Y chart that developed in 74 or something. That everybody's familiar with. You have three domains: behavior domains, the structural domain, and the geometrical domain. So in each domain you have so it's kind of not intuitive to look at, but it helps visualize or understand. When you have a chip and a complex design, you have different views, and where are they? You have layout, you have transistor, you have algorithm, you have leaf cells. you need to know why there's such a madness, and this help explain. But because of the time, I won't go into details. But I encourage you to see it. So behavior, you see algorithm in behavioral domain. In the structure domain means a processor. Is that a processor? Yeah. Sorry if it's so small to see, but in structure domain or in the physical domain, geometrical domain, structure domain, a processor, and here is a chip floor plan. This is where we are. We're in a physical domain, but we at a chip means when we do floor planning, we add the processor or the algorithm in the behavior domain. So you go through the module, and you go to the cell, and you go to the mass, meaning transistor. So this is transistor, right? In the physical, it's a mass, it's a layout, but in the structure is a transistor. But in the behavior, it's just zeros and ones. So this helped you visualize your level of abstraction in various domains. And to me, when I started, I knew nothing about this. I just went in and I designed at the transistor level. My first project was an embedded dynamic RAM. I jumped right into capacitor and transistor. I never knew all these things, but we tend to be bottom up. But it's fun to just understand top down. So this is a key concept of abstraction. It allows you to do, say, an effective means of dealing with design complexity, right? Creating a model at a higher level of abstraction involves replacing detail at the lower level with simplification. What does it mean? It means that at certain level, at higher level, you hide the details. So you don't need to know the details when you're at certain level. So you do that, you abstract it. Then you do that allows you to run faster and allows you to only look at things that are important at that level of design. So this is a detail, and just quickly, and everybody knows about this, right? At the processor level, you see block diagram is processor, RAM, ROMs, IOs, behavior, you represent them as equations. And then at register level, you represent them with register, and with some logic, and do register to register. And then you go to logic level, where you represent them with gates, Boolean gates, right? NAND, NOR, inverter, flip-flops. Transistor, go down to the transistor, and your layout, which is a physical representation of the transistors. So these things you guys can read. But just visually, these are the different level of abstraction that of the same thing, of the whole chip, but you have different level of abstractions. So I'll let you read these. But this is another way of looking at it. I find it useful because you see the real world and you say, why is it related to transistor? Why is it related to the CMOS and transistor and P transistor? This is why you have behavior, you have abstraction, behavior down all the way to physics. This is a real world you manufacture with physics. The physics start with this transistor. And this transistor, why it represents 0 and 1? Because of the voltage control gate, that because of the doping of these two regions, and you already should know all these things. It's just a switch, meaning depending on the voltage on the gate, either on or off. Right? On or off can be used to represent like a truth table. A truth table really implement a logic gate. So with Boolean algebra, so you go from physical, from a piece of silicon to Boolean algebra. Meaning transistor meaning 0 and 1s, and you go 0 and 1, and you go to Boolean. But you go to the other side, you see Boolean can be used to build the real world system. The real world system, this is for an example of like a digital signal processing. You have real world signal, audio coming in, RF or microphone. You convert those into digital signals, and then from digital signal you process it, and then you convert back to analog, to the real world, and you go out. So basically, the real world is analog, and then you sample it, sigma, delta, whatever, and then you have a digital representation of the data coming in. This is where I started my career. I started to design a DSP for the first, I started in 1980s when Motorola was ahead of everyone in cellular phone. So the DSP system, you go through ADC, and then you convert them to zeros and ones, and then you do FFT, you do all kind of signal processing, you clean up, you have a very good signal coming out, but basically you're representing the analog into zeros and ones, right? And if you look at the higher level system, like you have a computer or you have a cell phone, wherever, when you execute programs that are at a high level, but through a compiler and linkers, you transfer from high level languages into zeros and one binary, a machine language, right? And even with the typical microprocessor or processing system, like a Harvard model, where you have instruction memories and you have data memories and you have arithmetic, logical unit, control unit. You do all these things, the memories are really zeros and ones. So everything go into, from the real world with the typical microprocessor architecture. You do fetch, decode, execute, and store. Everything here can be done, translated into machine codes, which are really zeros and one. So and all zeros and one Boolean algebra can be used to represent a system, or to implement some function that does something in the real world. So with all these things, design level of abstractions, just some backdrop so that you understand what you're doing instead of just pushing buttons, right? Like a lot of people do. So now on the back end, there's some terminologies, right? When you're back end, you see both of these produce the gate level representation of the design, but logic synthesis still deal with speed and power. But at the gate level, at this gate level, the parasitic, the actual R's and C's at the logical level here is not known yet. But the reason why you want to do this one with estimated parasitic is because it has a higher level of optimization, where you choose the data paths and you choose the different building blocks based on the need for speed. So you will pick like a carry look ahead adder instead of what do you call like a ripple carry adder. If you don't need the speed, then you pick the simple building block to save your area and power. But if you look at everything, then the speed of operation here becomes too much, and so you divide and conquer by say at this logic synthesis, you estimate the parasitic and give me a good gate level netlist, and in physical design I do more and understand more, and you see what they do here. But basically, to answer the question of PPA and all. But physical design is the last step. After we're done, we send the mask to the fabrication. So what we do is really important, that a lot of people, because of their approach, they're pretty much just like a polygon pusher, but that's not about physical design. About physical design is really very high level skill. And some terminology here, because you can see people defining different things, for the physical design. Some people say physical design involves logic synthesis. Some people say physical design just place and route. But this is the definition we're comfortable with: logic, synthesis, place and route, parasitic extraction, and sign-off. They are we call back-end design digital implementation, because right now, this time, you're not really in the logical side, you're not designing, but you're implementing a logic. But you use the word physical design here because you're really designing, your transistor here. So you still do a design. And the circuit design is kind of part of it for very high speed functionalities that the standard approach might not be good enough. Then you do your custom design. And also circuit design is used to build the IPs, the foundational IPs, and all these custom blocks that you use on the higher level for your flow. So in here you can define basic backend design. Sometimes you call it digital implementation, and it's involved synthesis and place and route. But physical design, synthesis and physical design. So physical design we reserve for just place and route, extraction, and sign off. So that's physical design. But the core of physical design is what we call place and route, as you're familiar with. Okay, so those are the terminology. So this brings to, I think this is the last slide. Okay, so brings to what really the physical design is about. So this is what will we cover in your class, right? So the to meet all the goals that we mentioned, the approach for placing route and with a lot of methodologies that we mentioned, design principles, it breaks down into these steps in physical design or placing route. So at first we will do the import. Meaning that whatever is needed to transform a gate level netlist into a final output that you go to the fab, you send to the fab. So what does it entail? Meaning you import the building blocks are obviously the gate level netlist from the previous logic synthesis, and you have the cell abstract. This is a level of abstraction that when you didn't place and route, there are certain things you need only, and the rest of them you don't, and you know what they are in the next week. And then you to be able to know what you do, how you meet all your requirements, you have to put in constraints. Hey, what do I need to do to tell you that I'm done? So there are timing constraints that you're going to learn what they are, that drive the input, and the process, and also the physical constraints. You have a chip, you cannot make it too big if it has to fit in iPhone 17. There's some footprint that is designed by the board level. There's some physical constraints that you need to have your chip conform into. So all these inputs, you prepare them, and then you go through the process called import. So you import these input, and during this import, you read and check the quality of the inputs. This is very important because if you have incomplete constraints, you have the wrong cell abstract, you have the bad gate level netlist, you go through this and garbage in, garbage out, you will see things that really just doesn't make sense, and you waste a lot of time. So checking the quality of input is very important. When you read in, there are different things that you do to check, and then you drive it into a DB database, and you call it, name it, an import to identify the database. So at the end, what you wanted to know is that all the inputs are valid, all the constraints are complete. Complete is very important on the constraints. If you specify the constraints and then you miss some of the important constraints, your design come out, but at the end it doesn't meet the constraint, meaning it needs to be thrown back because you don't put everything in, but you learn how missing constraints are, what are the typical things that you need to check. So that's the first step. And after you make sure that everything is good, you go through the next process called floor planning. So floor planning involves you define the boundary of your design, like how big, how is the die size, where different things are, where the different IOs, pins should be, where the standard cells should be, where the micro custom power custom blocks should be, and then you do something called power planning or creating the power distribution structure. You learn about why this is important. And also, so this is called floor planning. Just like you building a house, you say this is my restroom, this is my kitchen and everything. So you organize different type of cells in different areas of the chip, and you complete. You say that's a floor plan. But the goal of the floor plan is to make sure that you fit everything in the area, but the design has to be routable. You learn what routable means. And then you have to have IR drop below limits. You learn what IR drops are, but you know from the context of physical design what they are. And time enclosure is feasible because of all different reasons and because of locality. So if you have a bus that is longer than minimum, you cannot meet timing, etc. So floor planning it affects a lot of stuff. A bad floor plan will result in enclosable argument. Your design doesn't have a chance to meet the performance goals. So floor planning involves a lot of knowledge about what you need to do as a chip at the end. So after floor planning, you do a placement. Placement meaning this is the optimization where you have a lot of gates and macros and everything. And you kind of say, okay, feasibly, I can meet timing, but now you have to arrange the gates so that your design will meet timing, and you have to resize the gate, restructure, implement different kind of building blocks. At the end, you say, is a design routable? Is design does a design meet timing, and is a power consumption is minimized? By this time, you have visibilities into RCs that are the parasitic things related to routing and all. You have more visibility than the synthesis. But at this time, you still don't have the route, the physical wise yet. You still estimating, but you're estimating with more details here, and you have more optimization here. And then you go through the process of clock tree synthesis. So clock tree synthesis, so every system, most of the system are synchronous. It means it requires some clocks. And then the clocks, the structure of the clocks, the timing, the edges of the clocks is affect a ton of stuff. So before you go to routing, you have to build a clock tree. You learn what it means, right? But basically, the build of the clock trees with managing different parameters help you achieve timing better, right? So you learn all these parameters that you need to optimize during this process. Without them, you have harder time of meeting timing. So you go through, learn that, and then finally, this is where you put all the wires, right? You put all the shapes, and then you expose to real parasitic, and the real parasitic will slow you down, will make your power go higher, etc. So this time when you do this, you actually have to conform to design rule errors. You know what they are, but by this time when you say no timing violations, really this is the final timing versus some level of estimation up here. And then your IR drops are real, your power are real, your design is reliable for real, manufacturable for real. So this is your final push, and this is the most accurate version of all your performances. And And this is an iteration process, meaning you don't just go from A to B and C, D, and then you're done. You just go, and each step you say, oh, I cannot meet timing. I'm going to have to go back and rearrange or re-optimize. So this is iteration process, but basically it goes through these steps. At the end of routing, you meet everything, you export out the output, and you analyze a QOR. You learn QOR is quality of results. So anybody can do a design, but a design is good enough. Vietnam has done a lot of microprocessor. We done 8-bit, 32-bit, 64-bit, but at the end we have hard time selling them because of the quality. So anybody can do a design, can push through the tool and do a design, but design is commercially good, requires a lot of knowledge from high level to lower level. So at the end, you will analyze all the results and quality, and you have to go back if the quality is not good enough. But the end, all the performance goals are good. You're ready to you do the verification step, and you go to the fabs. You learn what the verification steps are in general in the next lecture. But that's it for today. So I hope that is useful, and I don't think we have time for questions, but what we're gonna do is, these are just references. Mostly we use the images, and we don't have time to write them, so we use them whatever we can find. But you see a lot of references to this Professor Adam Tiemann. I found this very useful in terms of flip. You see a lot of videos from him that I refer you to read. So we use this real good professor to teach you. I mean, you watch his video, you watch his slides. So we're not as good as he is, but we use his stuff, and you will be reading, watching, and all. And we use all these, well-known, David Harris. He has online stuff. Professor Raby from UC Berkeley, and West and Harris. This is the Bible of the physical design and so on. So this is just to protect us from having used all these images. So this is just for your reference about trisomy. But yeah, so basically just a quick introduction to you so that you have an understanding of what the physical design is about. So like I said, we're going to refer you to, so expect some email with information on the Google Classroom, so where you can go in and get all the assignment that you can read and watch beforehand, so before the next lecture. So that's it. All right. Dave, Vũ, Thiện, Bạch, Bảo, anything else we want to cover, and Tuấn, if he's still here, before we let people to go. Sorry, we don't have time for a question because of all this introduction, but next time we'll have a lot more interaction with you, right? So.
Thank you. Thank you.
Thank you.
Okay. Oh, I'm glad we are in time, and we'll look forward to your questions and feedback. Okay. Vũ, but any or Dave, any final words before we end?
So I noticed
Sorry, can't hear you.
Không có log into Zoom thì ở đây Dave and I is gonna hướng dẫn cái sinh viên log into Zoom next time có gì thì interact được.
Oh, that reminds me, people wanted to have some pictures, but I guess we recorded it. Maybe we can extract picture from there, because the ban tổ chức wanted some picture as a souvenir for our start of the class. So.
I got a lot of picture from Da Nang and Ho Chi Minh City already.
Awesome, anh Tuấn. Okay, good. Good. So we don't need to do anything on picture.
Yeah, I got a lot. I think that I got enough, and the secretary board is already prepared. How to say an article for a today event, and will be public soon. So may I add somewhat before we leave?
Sorry.
Để em nói thêm với các bạn sinh viên một chút, tức là
Nói, muốn
vâng, tức
muốn nói gì?
là và mình muốn chia sẻ với các bạn, tức là cái cách thức ở đây cũng là cái chia sẻ với các đồng nghiệp ở Đà Nẵng và thành phố Hồ Chí Minh nữa. Thì ở ngoài Bắc này là hôm qua chúng tôi đã họp và thống nhất cái cách thức là sẽ tôn trọng và theo cái hình thức là flip class, nghĩa là sẽ tôn trọng tuyệt đối cái tính tự học và khuyến khích cái tính tự học, học thầy không bằng học bạn của các bạn sinh viên. Nghĩa là các bạn sinh viên có câu hỏi và có tương tác với TA, với instructor, nhưng mà đặc biệt là trong các buổi lab ấy thì chúng tôi cũng đã quyết định là sẽ dành một thời gian cuối buổi để các bạn có thể tự bàn, tự giải quyết những câu hỏi, và cuối buổi thì các bạn sẽ tập hợp những câu hỏi mà có cái sự trùng nhau và có chất lượng nhất để gửi về các cái hòm email của các cái thầy mà hướng dẫn ở Đà Nẵng, thành phố Hồ Chí Minh hoặc Hà Nội. Sau đấy thì chúng tôi sẽ có các buổi họp vào buổi tối và trao đổi với những nội dung đấy, bởi vì là khi mà chúng ta tương tác như thế thì có thể cái kiến thức nó sẽ được phát triển, nhưng chúng ta cần những câu hỏi và chúng tôi sẽ trả lời với các bạn. Ví dụ như ở Hà Nội chẳng hạn thì chúng ta sẽ có buổi lab ở chiều ngày thứ tư. Ngày thứ tư và cuối buổi các bạn gửi về cho chúng tôi thì đến ngày tối tối ngày thứ sáu chẳng hạn thì chúng tôi sẽ trao đổi với các bạn về cái nội dung đó. Và khi mà các bạn vào cái buổi lab ngày thứ bảy ấy thì các bạn gửi cho chúng tôi vào ngày chủ nhật, và ở tối ngày thứ hai thì chúng tôi dự kiến là sẽ họp với các bạn vào trước 10 giờ tối. Mỗi một buổi họp khoảng 30 phút để trả lời câu hỏi cho các bạn, cũng như là sẽ gợi ý cho các bạn những cái tài liệu mà các bạn sẽ chuẩn bị cho cái buổi học tiếp theo. Thế thì đấy là những cái mà chia sẻ thêm với các đồng nghiệp ở trong Đà Nẵng và thành phố Hồ Chí Minh. Ngoài ra thì các thầy sẽ vận dụng một cách linh hoạt cái cách quản lý lớp mình làm sao cho nó có hiệu quả. Và ở phía Hà Nội thì chúng tôi cũng đã lập danh sách các bạn học viên, sinh viên học tập ở phía Hà Nội, và chúng tôi sẽ ờ, ờ, gán trách nhiệm cho các bạn lớp trưởng, ban cán sự lớp, cũng như là các cái từng nhóm ấy, để các bạn sẽ tự điểm danh, các bạn sẽ tự đánh giá trong quá trình nào đấy, thì chúng tôi sẽ phổ biến một cách cụ thể sau. Và một lần nữa thì xin cảm ơn once again. I like to thank the instructor and TA from CHSME, and thank you very much for your participation.
Vâng, cảm ơn mọi người. Quý vị các bạn nhớ nhớ hỏi nhiều nha, và trong tương lai sẽ tương tác nhiều hơn, tức là sẽ có những câu hỏi mà mong muốn là sẽ có sự trả lời qua những cái poll của cái Zoom, thì qua sẽ trả lời sẽ giúp chúng tôi biết là như là mọi người hiểu không, hoặc là như thế nào, thì cũng hy vọng là mọi người sẽ có nhiều câu hỏi và là sẽ học được nhiều. Còn mà nếu mà không thấy mà không có kết quả thì cũng cho chúng tôi biết, cho nhóm anh Tuấn biết, để mà các thầy các cô có thể là giúp cho Trasemi giảng được giỏi hơn. Vậy thì xong Thôi, cảm ơn rất nhiều.
Cảm ơn các bạn, cảm ơn các anh. Bye bye, have
Dạ,
a good day. Chào thầy Hải, thầy
TA,
Sơn, anh Phiêu.
Cảm ơn
dạ,
anh Phiêu rất nhiều.
dạ mấy người cô
Thì
thầy,
cũng
nếu mà
sau
cô
cái
các
buổi
chị
học đầu tiên thì Bách Khoa Đà Nẵng cũng sẽ hội ý lại để có gì thì sẽ trao đổi thêm với ban tổ
Có gì
chức.
anh em mình trao đổi nha thầy Hải nhé.
ok, có thể là mình trao đổi sau. Thường thường là mình có cái debrief, nhưng mà chắc là mọi người bây giờ cũng khá lâu rồi, không biết mọi người có ở lại được không, có thể là lần sau đi, tại vì mỗi lần
Vâng, lần
học
sau
xong
đấy.
thầy cô là sẽ debrief một chút xíu trước khi mình về. Ok,
Em nghĩ là
như
sau
vậy.
cái buổi lab đâu nữa ấy, thưa có một buổi lý thuyết, một thực hành, thì mình sẽ tổ chức họp rút kinh nghiệm.
Ok, Cảm
Vâng.
ơn Tuấn, cảm ơn Hải Anh Sơn và cảm ơn mọi người rất nhiều. Chào tạm
Recording
biệt.
stopped.
Bye bye mọi người.
Dạ vâng, cảm ơn mọi người. Bye bye
Bye
mọi
bye.
người.
Have a good day. Have a good night.
Good night.
Thì các bạn ở đây thì các bạn là chưa biết chơi Google Classroom đó, thì có thể là đây sẽ hướng dẫn các bạn cho vào Google Classroom và
Dạ chắc mình gửi email nhiều hả?